let's take a look into this example. So determine the codebook vectors of a LBG vector quantizer for dimension n equals to 2 and the number of code vectors is m equals to 2 after one iteration for two vectors with the given training set. So this is our training set, is x, and then we'll have our initial codebook vectors are y1 and y2 given by this. So the training set, we're split this into two-dimensional vectors, so we get 3, 2, 4, 5, 7, 8, 8, 9. So the solution follows the algorithm which we explained previously. We start with the given randomly assigned codebook vectors y of k. The next step, we calculate the decision boundary b of k using the nearest neighbor rule to obtain the Voronoi region. So this results in a set of midpoints, and these midpoints form the Voronoi boundary line, which is perpendicular to the connecting line of two code words. So here is the direct midpoint b of k. So b of k in our case is the line going through the point 3 and 4, and the line consists of all points which have equal distance to the neighboring code vectors. Now we can draw the given training set vectors, the codebook vectors, and the Voronoi boundaries. So observe that the computation of the boundary line of the midpoint is useful only for drawing the picture. Yeah? In a computational implementation, we don't need to compute it. Yeah? We just need to use the nearest neighbor rule. So here is a pie plot. We have here our train set. So we split this sequence of numbers into vectors with two dimensions. So that's what we're doing here. So we will have here this y1, this codebook vectors y1 and y2, which is also defined here. So then we have this plotting here, just formatting to have a scatter plot here. So we have this picture here. So we have the Voronoi region 1 and the Voronoi region 2. So we see here, for example, this is the point 3 and 2. So this is our training set x, 3 and 2, 4 and 5. So we have here 3 and 2, 4 and 5, and we had our code books y. So we have 1 and 2, 5 and 6, which is given here, and then we're just plotting here the Voronoi region. So we calculate a boundary using the nearest neighbor rule, and we have these two regions here. So the step 3, we have to compute the new code words y of k as a centroid or conditional expectation over a quantization area. That is our Voronoi region. So in order to do that, we use this formula right here. So in order to find out in which Voronoi region a vector is located, we use the nearest neighbor rule, and for that we need to calculate the Euclidean distances between all the training set vectors and codebook vectors, and then we decide which training vectors are closer to which codebook vectors. So we will start with the first training set, and we will calculate the distance to the codebook vector y1, and we calculate the distance to the codebook vector y2, and we see that y1 is closer to the training set vector x1. Then we move to training set x2, we calculate distance to vector y1, distance to vector y2, and we see that y2 is closer. We move to the next training set, we calculate the distances, and we see which codebook vector is closer until we've gone through all the training set vectors. And now we can compute the centroid or the conditional expectation for each of the two Voronoi regions. So we've seen that for Voronoi region 1, we had only the training set vector x1. So its centroid or the new codebook vector is identical to x1, and we get the new codebook vector 1 as y of 1 is 3 and 2. But for Voronoi region 2, it contains the 3 remaining vectors. So what we do, we obtain its centroid by averaging over them. So we obtain our new codebook vector 2 as the average. And then if we update our plot, we see now that the new codebook vector, so this one is moving to this one here. So we are in Voronoi region 1, and as we calculated here, the new codebook vector becomes the set x1, so it moves to here. And for Voronoi region 2, it goes down, the value is 6 plus a third and 7 plus a third, so we have here, it was originally here, so it goes 6 plus a third, and then here we had 7 plus a third, so it moves there. And then we can draw a new boundary line here, and then we go back to step 2 and we'll repeat this procedure until the result does not change anymore.